For half a century, human spaceflight has been confined to low Earth orbit. That changes when NASA sends humans back to the moon. But they aren't going straight to the surface. They need to prove the orbital technology works before they can attempt the Artemis 3 lunar landing. The vehicle for this test is the Space Launch System, or SLS. Standing nearly 100 meters tall, it produces 15% more thrust during launch than the Apollo-era Saturn V. Perched on the very top is the Orion crew capsule, attached to the European service module. The service module acts as the ship's lungs, carrying the primary power, water, and propulsion systems. Artemis 2 is a 10-day stress test. The goal is to push this hardware into the deadly environment of deep space and verify it can keep a crew alive. To run those tests, NASA has assembled a 4-person crew with a strict chain of command. Commander Reed Wiseman serves as the primary decision-maker. Alongside him is pilot Victor Glover, who is responsible for the manual flying of the spacecraft. They are joined by 2 mission specialists, Christina Koch, an engineer who will become the first woman to fly to the moon, and Jeremy Hansen, who will become the first Canadian to make the journey. This roster replaces the solo nation test pilots of the Apollo era with a diverse international coalition. Operating a permanent lunar base requires global cooperation, and that starts with the crew makeup. After liftoff and the separation of the rocket stages, Orion settles into high Earth parking orbit. Here, they run their very first major system checks. Next is the proximity operations demonstration. Pilot Victor Glover now takes manual control, flying Orion around the discarded upper stage of the rocket to see exactly how the capsule handles in close quarters. Once they pass that test, they perform the translunar injection burn. This diagram maps the free return trajectory they take toward the moon. By using the gravity of both the Earth and the moon as a slingshot, they ensure Orion will naturally pull back toward home without needing any major engine turns. Proving they can manually pilot the ship and successfully lock into a safe return path are strict and essential safety prerequisites. NASA needs hard data that Orion can maneuver precisely before they let a future crew try docking with a lander in lunar orbit. During the outbound transit, the astronauts adapt to living inside the Orion crew module. They have about 60% more usable volume than the Apollo astronauts did, but it is still an incredibly tight space for 4 people to share for 10 days. Looking at the schematic of the Universal Waste Management System, you can see how they handle sanitation. Because of microgravity, this compact toilet relies on airflow to manage and contain waste. To fight the physical degradation of spaceflight, they have to exercise daily. This illustration shows the power-free flywheel device mounted inside the cabin, allowing the crew to perform rowing and resistance workouts. They also run emergency drills. This diagram details the bright orange Orion Crew Survival System suit. The crew practices rapidly donning and pressurizing these suits, which are designed to act as personal, miniature spacecraft if the main cabin ever loses pressure. Testing these specific life support systems and emergency protocols in deep space separates a short-term orbital visit from the sustainable habitat required for Artemis 3. On day 6, the mission reaches its climax. Orion swings around the heavily cratered far side of the moon, passing closely within 4,600 miles of the lunar surface. Here, they test the Orion Optical Communication System. Instead of standard radio waves, this system uses the Deep Space Network and lasers to transmit massive amounts of data, including 4K video, back to Earth at high speeds. But as Orion travels behind the moon, the physical mass of the rock blocks all signals. For 30 to 50 tense minutes, the crew endures a total communications blackout. During that silence, Orion must rely entirely on its autonomous systems to keep the crew safe. Surviving that blackout and successfully beaming high-density data via laser back to Earth proves we have the communication infrastructure to run a future lunar surface base. The return trip culminates in re-entry. This graph tracks the physics. The crew module hits the atmosphere at 40,000 kilometers per hour, Mach 32. Friction compresses the atmosphere, creating a glowing plasma shield. Temperatures spike to 3,000 degrees, triggering a communications blackout. To survive, Orion relies on the world's largest ablative heat shield. The material is engineered to intentionally burn away, carrying the extreme heat off into the atmosphere and insulating the crew inside. Bringing a crew back from deep space requires bleeding off massive amounts of orbital velocity. Proving the physical integrity of this heat shield under real-world stress is the ultimate hurdle to clear before returning astronauts from the lunar surface. Once Orion punches through the upper atmosphere and bleeds off its speed, a sequence of parachutes deploys, gently lowering the capsule to a splashdown in the Pacific Ocean for Navy recovery. The mission doesn't end in the water. Engineers retrieve the capsule to analyze the exact heat shield charring, the life support vent lines, and overall structural fatigue. That hard data provides the foundation for the next flight. By surviving deep space and withstanding re-entry, Artemis 2 proves we possess the technology to land humans on the moon and stay there.